As I said, when we talk about quantifiers, the quantifiers and the propositional functions or the predicates, they don't have to involve just one variable. So we can define quantifiers and propositional functions and predicates on as many variables as we want. So for example, I can talk about for all x and for all y, p of x, y is true. This basically evaluates to true if no matter what x you take, no matter what y you take from the domain of discourse, then the statement is true. Notice that x and y, they don't have to be necessarily from the same domain of discourse. Usually our statements would involve the same, but in theory nothing forces them to be the same. So I can talk about for all x that are real numbers and for all y that are integers, and then I can talk about p of x, y. Okay, so how they evaluate to true or false, just as before, but we now need to think about, let's say, 2 values or 3 values or whatever number of variables we have there. So let's look at these cases here. So the first one is saying for all integers m and for all integers n, 2 times the maximum of the two numbers m and n is greater than or equal to m plus n. So what we are saying here is that suppose you take any two integers, take any two arbitrary integers, m and n, and look at their sum, m plus n, then look at the maximum of these two and multiply that by 2. Is it always true that 2 times the max is greater than or equal to m plus n? Let's take m and n. Let's, for example, m is 10. Let's take m is 10 and n is 15. So we have m plus n, 25. 2 times the max of these two numbers is 2 times 15, which is 30, right? And 30 is greater than or equal to 25, right? Of course, this is not a proof because the statement is not saying there exists an m and there exists an n. It's saying for every m and n, is this true? If you think about it carefully, in fact, you can prove it because the maximum of m and n is greater than or equal to m and greater than or equal to n, and we can replace the sum by the greater of the two. So this is always true. It's impossible to find two integers. It's impossible to find two integers whose sum is greater than 2 times the maximum of the two integers. Let's look at the second one here. It's saying that if you look at any two integers m and n, if m is greater than n, then 2m is greater than n. Okay, so let's look at again the same thing. Let's say here now m is 15 and n is 10. Of course, m is greater than n in this case. 2m is 30 and it is greater than or equal to 10. It seems to be correct. It seems to be right. But is this always right? The answer is no. Again, keep in mind that integers include the negative numbers, and let's look at m being, let's say, minus 2 and n is minus 3, right? So if m is minus 2 and n is minus 3, then m is greater than or equal to n. Minus 2 is greater than or equal to minus 3. But what about 2m? 2m is minus 4. Is minus 4 greater than or equal to minus 3? This is false, right? So this is false, this is true. True implies false. This statement is false, right? So therefore, this one here, this statement is false. It is not true that no matter what two integers you take, if m is greater than n, then 2m is greater than or equal to n. This does not apply in particular for the negative numbers. Okay, for positive numbers, this is a true statement, and even if either one of them is 0, it's true. But once we go to the negative numbers, we can find counter examples to such a statement. Okay. If I look now at the two quantifiers being existential, so in the previous slide we saw for all x, for all y. Now we are talking about there exists an x, there exists a y, such that p of x, y. So now we are saying, can you find two values of x and y, not necessarily different, not necessarily equal, two values from the domain of discourse, such that p of x and p of xy is true? So, for example, let's look at this. There exist two integers, m and n, such that 2 times the max of these two numbers is smaller than m plus n. As we said on the previous slide, it's impossible to find two integers whose sum is greater than 2 times the max of this. This turns out to be false, actually. You cannot try any two integers m and n. You can try and you will see that you will fail no matter what m and n you take. The second one is there exists an n such that if m is greater than or equal to n, then 2m is greater than or equal to n. This statement is true, unlike on the previous slide where it was universally quantified. Now it's existentially quantified. So we are saying, can you find two integers m and n such that m is greater than n, greater than or equal to n, and 2m is greater than or equal to n? The answer is yes. Take m to be 5 and n to be 1. M greater than or equal to n, this is true. And 2m, which is 10, greater than or equal to 1, which is also true. True implies true. This entire proposition here is true. So this is true. And the proof for that is take m to be 5 and n to be 1. Okay? Because all we care about is, can we find one integer m and one integer n such that the predicate holds? Now, we can also have different types of quantifiers in the same statement, right? So we can talk about for all x there exists a y. Now you have to be careful because the order of these quantifiers starts playing a role there. So I'm talking about when I say for all x there exists a y, think about it like this. No matter if you take an arbitrary value of x, can you find a specific y for that x? Can you find a specific y that will work for that x to make p of x, y true? If you can, this entire statement is true. If you can't, this statement is false. So if you look at the first one, think about it in English. What is it saying? For all m, there exists an n such that m plus n equals 0. So is it true that if I take an integer m, I can find an integer n such that m plus n equals 0? The answer is yes, because we can always take the negative of the number. So if you give me an m, if you give me a number m, I can give you n being minus m. And if you take the sum of them, it is 0. So this statement here is true, right? If you think about it, if it was for all m, there exists an n such that m plus n equals 0, but the domain of discourse was the natural numbers greater than or equal to 1. Is this true? The answer is no, because if you take 5, take m equal 5, what natural number can you add to 5 to make it 0? There is no such number, right? Because natural numbers do not include the negative numbers. So if the domain of discourse was the natural numbers, this statement is false. The second statement here says that for every integer m, there is an integer n such that m is greater than n squared. Now think about it carefully here. N squared is always positive or 0. In the when n is 0, it is 0. But for every other number, n squared is positive. So is it true that every integer is greater than non-negative number? The answer is no, because if you take m to be minus 10, there is no n such that minus 10 is greater than or equal to n squared. N squared, again, it's either 0 or a larger number, and minus 10 cannot be greater than that. Therefore, this is false. Okay? So, again, this is the statement where I'm saying for every x, there exists a specific y for that x. I can flip the order and say there exists an x such that for every y, p of x, y is true. So I'm talking about a specific x. Does there exist a specific x that no matter what y we take, p of x, y is true? So let's look at the first one. Does there exist an m, an integer m, such that for every n squared is greater than m? So does there exist an integer that is smaller than every possible n squared? The answer is yes. You can take any negative number m. So take m to be minus 1000. Take every integer n squared is definitely greater than minus 1000, because I know n squared is at least 0, right? So it has to be greater than minus 1000. So this statement is true. The second one, we are saying, does there exist an integer m such that for all n, mn equals n? Okay, so is there a number that no matter what number you multiply by it, you get that number? So let's say if you take m to be 2, this is not true, because then if m is 2, 2 times 3 is not equal to 3, right? But can I find m? Usually the numbers in these kind of cases that one thing about are either 1 or 0. If m is 1, this, for example, works, because if you take m to be 1, 1 times n equals n, right? So this case here is that if you look at if you take m to be 1, if you take any integer n and multiply it by m, you get that n back, right? So there is that specific integer, some magic number m, that no matter what number you multiply by it, you don't change that number, right? And that's 1. So this statement is true here, okay? And it's very important to notice that when we have the same types of quantifiers, so for example, for all x, for all y, swapping the order doesn't matter. So for all x, for all y, and for all y, for all x are the same. The same thing with existential quantifiers. However, we have shown examples where swapping the order when you have different types of quantifiers is not safe always. Sometimes you lead to two different statements. So for all x, there exists y, and there exists y such that for all x are not necessarily always the same. There could be cases where these two statements could be true, but in general, that's not the case. The last word I want to say here is about negating nested quantifiers. So what happens when I have negation of multiple quantifiers there? Remember that I talked about De Morgan's laws for quantifiers. We said that the negation of for all x, p of x, is equivalent to there exists an x such that not p of x, and not there exists x, p of x, is equivalent to for all x, not p of x. Similar thing here we can do. The simple way to think about it is push the negation all the way across all the quantifiers until you get to the propositional function. And as you come across one of the quantifiers, if it is universal, flip it to existential. If it is existential, flip it to universal. So if I look at the first one, I want to start moving the negation inside. I hit the for all x, I turn it to there exists x. I hit there exists y, I turn it to for all y. I hit there exists z, I turn it to for all z. I hit for all w, I turn it into there exists w. Negation of p, x, y, z, w. This is how we can negate these kind of statements. Same thing for the second one. For example, I take the negation across, all of them are universal, all of them turn into existential. So this becomes there exists x, there exists y, there exists z, such that the negation of x, y, z. The last one, not all of them, but the first three are existential. They all turn into universal. Last is universal, turn into existential. And then notice that there is negation before the r. So then we get to double negations and they cancel out. So this becomes for all x, for all y, for all z, there exists w, such that negation of r, this becomes. Okay. So it's a very simple way of thinking about negating statements that have nested quantifiers in them. And this actually wraps up our discussion of quantified formulas and how to have them in a nested format and what happens when we negate them.